In this video, we're going to be doing a rotational equilibrium FRQ practice. So a uniform horizontal beam of length 6 meters and mass of 12 kilograms is attached to a wall by a pivot at the left end. The beam is held in equilibrium by a cable attached to the right end, which makes an angle of 30 degrees above the horizontal. Two masses are attached to the beam. So let's draw this. That is our pivot. There is a cable at the right end. This is 6 meters. So and then at 2 meters, you have a 5 kilogram mass. At 4 meters, you have a 10 kilogram mass. And this is going to be our weight 1. This is going to be our weight 2. The tension is at the end here, and this angle is 30 degrees. So now you can draw this out. This is also going to be 30 degrees here. So our weights are all going to be acting clockwise. And our tension is this, and it's going to be going through here, so it's going to make it go counterclockwise. So you start off with your rotational equilibrium. Let's write down what we have. This length is 6.0 meters. Your mass of your beam is 12 kilograms. So your weight of your beam is going to be 12 times 10, because we assume it's just 10 here. That's going to be 120 newtons. M1 is 5 kilograms. So that means your weight 1 is equal to 50 newtons. Your M2, or weight 2, is going to be 100 newtons. Because your mass was 10 kilograms, our cable angle is 30 degrees. So for our FBD on the beam, it would say we'd have weight 1 here. We would have a weight 2 here. And then you would also have your weight of your beam here. at the center of mass. Your tension force at 6 meters angled at 30 degrees, you would have, on the official test, you would not break it into components. So you would have your T here, but here you would have a Ty and a Tx. Tx is equal to T cosine of theta, which is T cosine of 30 degrees, because our angle is here, right? So you would look at your adjacent, which would be equal to this. So you would be given, you have your wall, and you would have your hypotenuse here, which would be your tension. In order to get this side, you would look at the other two sides, and then here you would have, so this is your opposite, and then here for Ty, this would be sine 30 degrees, because this is going to be your opposite over your hypotenuse, your other two sides. So those are your tension forces. Your pivot also has forces as well, but the R is equal to 0. You would have AX and also AY. So your torque, though, would be 0. So let's solve for our tension in part B. Using rotational equilibrium, derive an expression for the tension in the cable. So if you have your summation of torques, your summation of torques. So we're going to choose our pivot to be at the very left. And if we do that, this is going to eliminate our AX and our AY. This is our strategy so that we have less values. So now we know that torque is equal to FR sine of theta. We know that all forces except for our tension are vertical. So torque is equal to FR. Now for tension, you have torque of tension is R F sine 30 degrees. Now we can make our setup. So rotational equilibrium means that the torque counterclockwise is equal to the torque clockwise. So now we're going to set everything up. Torque sine 30 degrees times 6 is going to be equal to 50 times 2 plus 120 times 3 times 100 times 4. So here this is equal to 100 plus 360 plus 400. So this is equal to 860. And then this is going to be sine of 30. This is going to be 3t. And then now you just divide both sides by 3. T is equal to approximately 287 newtons. So that's going to be your answer for part B. That was your FBD here. Now we're asked to determine the horizontal and vertical forces at the pivot. Write an equation to solve for AX and AY. So at the pivot, you have your AX and AY. So you have your summation of your horizontal forces is equal to 0. So you have AX minus your tension, and your cosine is going to be your horizontal tension, and that's equal to 0. So your pivot is going in, its AX is going to the right, and then AY is going in the opposite direction. So you can write this as AX minus T cosine of 30 degrees. So AX is equal to T cosine of 30 degrees. If you plug in, this is going to be equal to 287 times 0.866, which is approximately going to be 249 newtons, because we got our tension force over here. Now, AY plus 287 times 0.5 minus 270 is equal to 0. AY plus 143.5 minus 270 is equal to 0. So AY is equal to 270 minus 143.5. That's equal to 126.5 newtons. So that's your AY and that's your AX. Suppose the cable is moved so that it makes a larger angle with the horizontal and is closer to the vertical, while all conditions remain the same. Explain how the tension in the cable changes and justify your answer using physics principle. We want a larger angle with the horizontal. So our torque from the cable is equal to R T sine theta. If theta increases, then sine theta increases. And you also have to maintain equilibrium. So T sine theta times R is going to be constant. If sine theta decreases or increases, T has to decrease. So as your angle becomes more vertical, your cable becomes more efficient at producing torque. So less tension is required. So your tension decreases as sine theta increases, so less force is needed to produce the same torque.